Okay, so thanks everyone for coming, and I guess also thanks to anyone who then listens to this later on. I'll quickly share my screen, and then we can get started. Okay, so you should be able to see my screen at this point, and I'll quickly go over a couple slides. So the point of this call is essentially just to go over some of the grants that have been approved for the EVM track of the verified zkEVM project. Some of the work has started, I think, especially on the runtime verification side. We also have a couple other teams who maintain formal specifications of the EVM, and obviously we'd like to make use of these later on, and also all of these specifications are useful for other applications as well. So we've figured it would be a good time to also bring these up and have an introduction to all of the formal spec that we have for the EVM, and especially obviously the execution layer of Ethereum has a few interesting quirks around the specification itself, in the sense there's maybe a bit of a lack of canonical specification, and we can talk about this later on. But the main thing is that we've got this big project running, and the aim is to formally verify these zkEVMs, which are EVMs running on zkEVMs. zkEVMs are pretty awesome. You can take, in principle, at least any program and prove its execution, which is nice through knowledge proof. And this implies that you can just take an EVM implementation and run it on a zkEVM and save yourself a lot of trouble, because you therefore no longer need to write a circuit for the EVM, which is what zk rollups have been doing for now with some of the issues that have come up.
Sorry,
yeah,
Alex. I don't think we can see your screen. It's doing some weird stuff.
Let me try and share it again. I'll try and share my screen in general rather than just the Firefox tab.
That works.
Is this better?
Yep.
Cool. Okay, so we've got these general purpose zkEVMs, which are awesome. You can run the EVM on them to some extent. And we're specifically interested in RISC-V zkEVMs, RISC-V being a nice, fairly established open source ISA, and which has kind of available compilers, which means you can compile your EVM to RISC-V, again, at least in principle. And one very specific thing is that if you look at the table on this slide, which has a nice list of all the zkEVMs, this is actually an old picture, there might be one missing. You'll be able to see fairly easily that, at least for RISC-V zkEVMs, the very dominant language that is supported is Rust, which is a bit unfortunate because Rust has a very nice implementation of the EVM in the form of revm, but obviously we have many, many more implementations of the EVM, which are used at the layer 1 level. And especially as native rollups start to come up, we might end up obviously relying on more clients than just revm. And for the sake of client diversity, which is useful not just for security, but also to actually generate different ideas and different approaches to implementing the EVM and ensuring that there's no vendor lock-in, it would be nice to be able to support more implementations of the EVM than just revm. And I'll get back to this a bit later on. Now, when it comes to verifying the EVM, we're pretty lucky to already have several formal specifications. I think Runtime Verification were the first one to really develop a formal spec in K. And then since then, we've also had recently a lean specification developed by Nethermind. There's an ATL2 specification developed by Kestrel. There's a whole 4 specification developed by Verifereum. And then with Rocq, formerly known as Rocq, we obviously have Karl and Bas's grant to develop a specification there, as well as Formaland's effort to show that the RVM is equivalent in some sense to the Python EVM spec using their Coq of Python and Coq of Rust tools. We also have some nice RISC-V formal specifications. The canonical RISC-V specification is the sales specification, which you can extract to Rocq or for Isabelle, and as of very recently, there's also a lean extraction that's close to being finished and being fairly polished. And then obviously K have their own RISC-V model, and there are a bunch of other RISC-V models floating around, including actually RISC-0 had a RISC-V model in lean that they developed kind of fairly early on. And there are other kind of handwritten models there. So we have a couple options to actually verify implementations of GEN. The first option, which is perhaps the simplest, would just be to verify the source code of an EVM implementation against the specification. But then you run into the issue of having to trust the compiler and trusting that once you've compiled your source code, which won't match specification, the compiler hasn't introduced a bug. And as we all know, these things happen. Option 2 to try and address this is to verify compiled code against the compiled specification, which helps avoid the issue of compiler bugs to the extent that you only suffer from compiler bugs if the same bug happens when compiling both the specification and the code you're interested in verifying. But obviously maintenance then becomes potentially quite difficult. And an open question there is how to keep this verification status live as the EVM constantly changes and then implementations constantly change as well. Option 3, which would offer, in principle, an easier path towards maintenance, is to actually just generate code from a specification and compile that through a verified compilation pipeline so that the code that you get matches the specification with a high level of assurance from that verified compilation pipeline. The downside here is potentially that it becomes a bit harder to get competitive performance because you're relying on a verified compiler, which might not have as many optimization passes as unverified compilers do. And in terms of the work that we're doing, we've got 2 grants that are live at the moment. The first grant went to Runtime Verification, and the goal there is to verify revm compiled to RISC-V against KEVM compiled to RISC-V, which is option 2 in the previous slide. And the second goal is also actually to develop a lean backend for K in order to check that KEVM and Nethermind Z specification are equivalent and give us a sense that we're not working off a flawed spec by accident. We've also got a second grant, which has gone to Bas at Aarhus and to Karl at KTH. And the goal there is actually just to develop a canonical specification in Rocq for the EVM and to try and just generate performant code that can be compiled via a certified compilation pipeline. And obviously the Rocq ecosystem has very specific expertise with certified compilation since they produced CompCert and Certicoq. And I think as far as proof of systems go, I don't think there are any other proof of systems that have the same amount of past work and therefore expertise on certified compilation. And we also have a few open questions and questions about future plans to address past these 2 grants. So with these 2 grants, we'll probably have a lot of work done towards verifying that RVM works as intended for a specification. And from the lean backend, we'll know that it follows the spec of both KEVM and lean's Nethermind specification and Nethermind's lean specification, which is nice. And we'll also potentially have a nice performance specification that follows from the Rocq specification that Karl and Bas will develop. But this only covers at most 2 implementations of the EVM and at most 2 sets of EVM precompiles. And there are many more EVMs to look at. So the first question there is obviously how to extend form verification to more implementations of the EVM. To some extent, this isn't the hardest thing in the world because we're lucky to have other teams that maintain formal specifications, and so we can repeat the same efforts as runtime verification are doing for other implementations of the EVM. But one question there is how to make this sustainable, both economically, because if you're trying to formally verify several different clients, you obviously run into the risk of going up to massive investments, and also making this sustainable in the sense of keeping track of changes to the EVM and making sure that if you do verify an implementation of the EVM, it stays verified as changes come. And there are a lot of big changes coming to the EVM in the next hard fork with EOF, if it makes it into the next hard fork. And with native rollups, we're looking at an execute, precompile, and things like this. there's potential SIMD precompiles, EVM max, and just a lot of changes that are coming to the EVM and will probably keep coming to the EVM, which will require effort both in terms of maintaining formal specifications, but also in terms of verifying the changes to implementations of the EVMs accordingly. The other important point is that obviously if we start verifying multiple different clients written in multiple different languages, even if they will compile to RISC-V, and we start using multiple different formal specifications for this purpose, it would be increasingly desirable to have some sense that all of these formal specifications are equivalent. To some extent, if you had all formal spec pass all of the conformance tests, we get quite a high level of assurance from this. But it might be nice to go a bit further and to extend the work that, for example, Runtime Verification is doing in showing equivalence with Nethermind gene specification, and getting this done for more specs that are going to be used, whether that's the Rocq specification, JCL2 specification, the whole 4 specification, and anything else that people come up with. Because one interesting point with all the different formal specifications is that they can have different benefits and be more or less better for different use cases, depending on the tooling that's available around the language that they're developed in, or the tooling that's built around them in the language that they're developed in, and access to other things in the language ecosystems that they're developed in. So Whole 4 also has some expertise with verified compilation, for example, and I'll let all of the different teams maintaining formal specifications talk a bit about their own specification and the kind of any unique benefits or quirks that set them apart. So this is more or less the agenda for today. We'll have runtime verification, and Bas and Karl from Aarhus and KTH will give a quick talk about their ongoing and planned work. We'll also then have an introduction to the other formal specifications of the EVM by the teams that are maintaining them, so that we can hopefully leave this meeting with everyone having a sense of what actually exists in terms of formal specifications and the different ecosystems that they're developed in. And then we can have a more general open discussion about open questions and about future plans. In particular, obviously, I think verifying other implementations of the EVM will be a big question, and to some extent, this obviously also depends on zkEVMs evolving to be able to run different implementations to EVM, especially implementations that aren't written in Rust. So that's it from me for now, and I'll leave the floor to runtime verification, and then Bas and Karl, and after that, the different formal spec teams.
Well, thanks, Alexander. I don't have slides, so I'm just going to talk, and I hope that's okay. And then folks can ask questions. Feel free to, please. I would make one small correction on the slide there. We're not compiling KEVM to RISC-V. We're actually just showing equivalence of KEVM to REVM compiled to RISC-V.
Yep.
Just to make that clear. So yeah, our goal is to show equivalence between KEVM, which is a formal specification of the EVM that's existed since 2017-ish, and it's been kept up to date with all the conformance tests and maintained throughout all that time. And REVM, which is the Rust implementation of the EVM. Specifically, there's a subcrate called, I think, REVM interpreter that we'll be comparing against. And then to EVM lean, which is Nethermind's lean model of the EVM. And so the approach we're taking is, first, we made an extractor from K definitions to lean 4. And I'm going to go into a little bit of technical detail here because maybe different components of this are interesting for other teams outside of us. The way we approach this lean 4 extraction is we built in Python a library for representing lean data, lean definitions structurally. So you can represent in Python as Python objects and classes and everything, a lean definition, and then basically just call the text method on that, and it prints out an entire lake project for you that should compile and run and build as long as the definitions that you've supplied are, valid lean. And so first we made that library for just building lean definitions, building lake projects in Python, and then we made something that takes the Python, data structure representation of a K definition and just translates it to one of these lean Python objects, and then just calls the text method and produces the lean definition. So maybe that Python module is interesting to some people here. Feel free to reach out and let us know. We tried to make it standalone. Right now, it's not in its own repository, but if the first time someone comes and says, hey, that sounds interesting, I could use that, we'll pull it out and do a separate repository and set up CI on it and everything. So we take what we're doing is taking KEVM, which is a small step operational semantics of the Ethereum virtual machine, and instructing it to symbolically execute each of the opcodes in the EVM just standalone against a fully symbolic state. So we say, hey, execute the add opcode for me against a fully symbolic state. And then it does that execution, and it has some branches like, oh, maybe the stack underflows, maybe the stack overflows, maybe you run out of gas, maybe it has a bunch of branches associated with that. But on one of those branches, it reaches the end of executing the add opcode. So you had enough items on the stack, you had enough gas, all the other checks passed, and you hit a new state where the stack is updated with the new value on the top and the two values removed, and the gas is deducted and everything appropriate there. So we made a tool for doing that sort of opcode level summarization in KEVM automatically and producing a new K rule that is just it's not a big step, but it's a medium step, I would say. We're going from a small step where each operation is done one at a time, like deduct gas, take item from stack, put item on stack, and going to a medium step where the whole opcode is done at once as a single K rule. Then we take that new definition we get, which is kind of like an optimized KEVM, if you think about it, and put it through the lean4 extractor, and now we have a lean4 definition of that optimized representation of KEVM, where each transition in this definition is a single opcode potential execution against a fully symbolic state. So that's kind of the starting point for both of the next projects, which is the equivalence with EVM lean and the equivalence with REVM. So the equivalence with EVM lean, we've made really good progress on at this point. Basically, how we're approaching that is we're making a function that takes one of these KEVM states that's represented in lean and maps it to an EVM lean state. So we do that for the pre and the post state of the KEVM states, and we map them both to the EVM lean state, and then we build a lean4 theorem that says, if I start in this pre-state in EVM lean and I do symbolic execution, I will end in this post-state in EVM lean. That's roughly the desired statement of the theorem. The actual details of how the theorem needs to be stated, that it gets a little bit hairier than that, right? So, but that's roughly, what we're approaching with the desired outcomes. And we have been working with the Nethermind team. We've made a couple suggestions of changes they could make to their semantics that would make this proof easier. Anyway, in terms of automation, the extraction of opcode summaries from KEVM all the way down to lean is fully automated for something like 85% of the opcodes at this point. And we just stopped at that point because the next 15% are pretty challenging. We wanted to work on other parts of the pipeline, and like the ones that do like calls and creates and stuff, we are going to wait until we have more of the pipeline for that. Then the mapping from the KEVM in lean4 state to the EVM lean state, that's also fully automated, right? Also, the statement of the needed theorem for each individual opcode is fully automated. Discharging those theorems, how we're planning on going about that is break down the opcodes into different classes of opcodes. Some of them are like arithmetic opcodes, some are memory opcodes, some are account opcodes, some are chain state opcodes, and see if we can have basically a different tactic for each class of opcodes. Like the arithmetic opcodes all look pretty similar. They take some items off the stack, they do an arithmetic operation, they put an item back on the stack, right? And so there, you really just need some arithmetic reasoning to show like, oh yeah, that's the expected value at the end. So basically break down into different classes and try to have kind of one general proof per class with maybe some specialization working for each one. We're not quite sure about that yet, but right now we're generating all the theorems and we've proven by hand, a handful of them, and we're factoring out common patterns basically in those proofs. So that's how far along the KEVM to EVM lean equivalence is. Now, if there's no questions, I'll talk about the KEVM to REVM equivalence and how we're approaching that. I'll give a quick little pause here. Okay, so with the REVM to KEVM equivalence approach, which should also establish some sort of relationship between REVM and EVM lean, our number one goal is the RISC-V that you get out of compiling REVM to RISC-V for the zkEVMs. I don't think it would be hard to target Rocq from K. K is a really simple language. It's great for modeling large definitions, but it's a really simple language. It's pretty easy to make embeddings in other languages. In fact, there is already a model of matching logic in Rocq. So as far as the so our goal is to show that REVM, if compiled to RISC-V, that RISC-V that you get out is what's equivalent to KEVM. And so that should be independent, that shouldn't matter if there's errors in the compiler, the compile tool chain from Rust to RISC-V. That's the goal there, right? And so what we're doing is we're compiling REVM to RISC-V, and then we're going to symbolically execute, again, each opcode one at a time on REVM on the K RISC-V semantics and collect this medium step of an opcode running in the EVM interpreter on RISC-V using K's symbolic execution. So that's kind of some inception going on there, but the point is to get basically again these K rule level summaries of this is what it means to execute the add opcode on REVM compiled to RISC-V. Then we'll take those K rule level summaries and again export them to Lean 4, where we already have the KEVM exported to Lean 4, and make a similar equivalence mapping between the KEVM in Lean 4 and the RISC-V REVM in Lean 4. This whole side of the project will be brittle, right? It's going to be the other side, the KEVM to EVM lean, I think will actually be fairly malleable to changes. Like it'll work well with changes to the specs. But the REVM RISC-V work will be brittle because the compiler could change, which would change the way that it lays the memory out on the RISC-V machine. It could, there's all sorts of things that could change basically because we have, an interpreter running in a VM. It's just becomes brittle. So we are thinking about how to address that, and one approach that we're thinking about is to somehow bring in the idea of property testing at the Rust level. Maybe not property testing isn't the right word, but something where we write a chunk of Rust code that basically says, set up the REVM interpreter crate, put dummy values where you need, maybe even fill in symbolic values if we take the approach that we take with like control, where we can put in symbolic values from the arguments of the functions, and then do what's called make a cut point, which instructs our tooling like, hey, save this symbolic state, whatever it is. Then execute that one opcode and make another cut point. And so now we have the state before the opcode and the state after the opcode as cut points, but we used Rust to do the setup rather than trying to do all the setup at the RISC-V memory level. And again, we don't have to mention at the Rust level, like how is the memory laid out or anything like that. So now instead of having something where we're trying to like look the RISC-V state and extract like, okay, this is where the stack is, this is where local memory is and stuff like that, we just have a delta between, a pre-state and a post-state that we know corresponds to executing that one opcode. And we were thinking maybe if we can get those deltas automatically, it can reduce the amount of work we have to do down at the RISC-V level. We're still doing the proof at the RISC-V level, but somehow it informs that proof and makes it a little more automatable, a little less brittle. We're still kind of fleshing out that idea. That project, we're just starting, and we're just starting to play around with the RISC-V that we're getting out of compiling REVM on our semantics, executing that on our semantics at this point. So that one's just starting. Open to ideas, though. I think that one's going to be pretty challenging. So thank you.
Okay, so should I go next, maybe?
Yeah, go ahead.
Okay, just 1 second here. Okay, I had some slides here. Damn it. Damn it. There's some issue. Okay, wait. I have to. Looks like I have to set things up better here. Sorry for the wait. Yeah, so this will not be very technical. This is just kind of giving you some background on what we're doing on the EVM side. And there we are. Okay, sorry for the wait. So I'm Karl, and I'm working with Bas here on this Coq side, or Rocq. So basically, the Rocq first release of Rocq is coming out, I think, in the next few days. But so I will sometimes slip back maybe to call it Coq, just for historical reasons. But yeah, so the motivation for this work is essentially more mundane than maybe technical. So there have been many kinds of formalizations of the EVM already in Coq, and the problem is that there are new ones popping up all the time. So essentially, people kind of pick pieces out of old formalizations and kind of make them into a new one, and suddenly you have n+1 different formalizations. And we're trying to kind of, I guess the pitch here was that essentially we're trying to do the canonical one, right? That hopefully others will be able to reuse and contribute instead of making their own. So I just gave some, for example, we had a colleague who recently kind of dug up this old formalization by Yuichi in LEM, and which can be exported to Coq, and then you have to sort of massage it quite a lot, and then it can compile. But it's not very idiomatic Coq, and it's not very, I would argue, not very maintainable. And then people are doing kind of research around like bytecode optimizations. They do kind of partial formalizations, not all of the bytecode instructions and so on, right? And this is just a some examples, right? I mean, if you sort of Google or search on GitHub, you'll find a lot more. So this is the kind of mess that we're trying to clean up here a little bit. And at least I feel that one of the most mature libraries in Coq is the mathematical components libraries. I would argue that it's even in many respects better than the Coq standard library, because it has kind of a conscious design. So it has a large collection of utility data structures and results, but it's also been used for very serious mathematical work. So, for example, the four-color theorem and odd order theorem and so on. So it has quite a lot of history, and the evolution is typically very slow. So they make very small backward compatible changes. So we hope that by basing an EVM formalization on top of it, it can, ensure the Rocq code keeps compiling over time and so on. So again, backward compatibility, and arguably, I think that this is the only actually maintained library for machine words or bytes or bit strings or whatever you want to call them, right? So there are others, but none of them are, to my knowledge, actively maintained. And also, this is something I've been helping to develop the last few years, is the Coq platform, or Rocq platform, which is a collection of many different libraries and plugins and so on for Rocq. And we do kind of a release for every big release of Coq. Every 6 months, there's a corresponding release of the platform, which has all these possibly 40, 50 plugins and libraries. So the aim here would be this formalization becomes part of this platform, and then it's going to be quite easy. So this prepares, everybody can kind of access it just by installing the Coq platform. So that's the goal here. So essentially, so mathcomp is not meant for executable code. So it even has a mechanism called locking, which is widely used, which prevents execution. So it's very much optimized for proof. And then what you do instead is that you make your definitions, and then you make nice theorems about them. And then it's basically by refinement or some other mechanism. So there is even a refinement framework using MathComp called KEVM. So that's how we're hoping to. So this EVM formalization will just be very high level, right? And then Bas hopefully can talk a bit more about how you get to compilation. So that's it. Any questions or comments here? Okay. So yeah.
So just to connect it to, to previous talks, as Karl mentioned, so that there is the Rocq backend for LEM, and LEM was designed with a similar motivation as the K framework. It's also related to the ODD tooling. So as Karl mentioned, so that one doesn't give idiomatic code, and it will be interesting to know what your experiences are with K and Lean. So that's more a question for Everett than for Karl, I think.
Yeah. So actually on the call with us is Tomasz, who made the Lean 4 backend. I think it'd be hard for us to compare it to generating to LEM. My understanding of the LEM model was it was never really complete or usable. It kind of modeled things that were calls or cross contract things as just like havocing the state, basically. That my understanding of that is also outdated, so I could just be wrong on that. Yeah, so we've tried a couple of different ways of embedding K into other interactive theorem provers. K has really emphasized the modeling language more than the proving capabilities, and that is because the first things that were built with K was a semantics of Java and a semantics of C, and so there it was, what was prioritized was being able to model really big programming languages, basically. And so while K does come with a prover and a symbolic execution engine, our goal has been always to be able to do some sort of interactive theorem proving in another framework with that. When we made an embedding in Rocq, which I sent a link to in the chat, that was a deep embedding, and so the approach there was to model matching logic, which is the underlying logic of K. It's kind of a very simple extension of first order logic. And so it's very good for SMT solvers. My opinion of that embedding is it was not super useful. I also didn't really try using it for much, and so I don't know. With this Lean 4 embedding, we're really going for much more of a shallow embedding and then build up a library of just doing K reasoning rather than trying to model matching logic in Lean 4. We're just trying to get, as idiomatic of Lean 4 as possible that you can, while keeping the semantics of the original K definition. There have been some challenges with that. One of the big challenges is K's pattern matching for applying rules for functions is really expressive, and it allows very expressive guards on the application of functions, and we couldn't really map that one-to-one to Lean's functions directly, which is unfortunate because then we lose some of the facilities for reasoning about functions that Lean has. But we were able to map it decently and also generate theorem stubs that bring back the full usefulness of functions if you prove those theorems as well about the generated code. So that's kind of a roundabout answer, but I'm happy to ramble some more.
Makes sense. I'll speak a bit about Hex. So I think we have similar issues and similar successes there. Thanks.
Yeah, so do you want to go next, Bas?
Yep. Can you see yeah, this seems to work. So here's our plan on getting a certified version of an EVM interpreter that runs on zkRISC. So the first step is what Karl has just presented. So to make a standardized EVM specification and interpreter using mathematical components. then the next ingredient is to use the certified compilation of general programs in Rocq. There's the MetaRocq and the certiCoq framework. So MetaRocq is doing Rocq in itself, and then certiCoq is using that framework to actually compile to a number of backends. So one compilation first go to some of the intermediate languages of the CompCert, the C compiler, verified C compiler, and from there one can go to x86, to RISC, to ARM. Another thing one can do is directly go from one of the intermediate languages, Lambda ANF, to WebAssembly. So that's something that we've done recently. We can probably reorganize some of these things to go to RISC-V in a more efficient way. There are some discussions about that at the moment. The important thing is that the compiler has been verified in Rocq, not just written in Rocq, as is my understanding of what the current status is of Lean. So sometimes people say that Lean has a verified compiler, but I think the guarantees in Rocq are much stronger. Ramana said just that, I mean, there's KEVM, which is a very big project of a verified compiler in whole 4 that has been verified in itself, which I think was one of the templates for certiCoq also. What we've done with certiCoq WASM is to target WebAssembly, and then this could be connected to the zkEVM framework that's already in Rocq. Now, of course, here in this project, we would like to target RISC-V, so we need to remodularize those parts, and we hope we can share code there. There's also, I mean, the ideas about what zk circuits should be done precisely. Each time I talk to Alex, I get new ideas of what's the latest, and we'll be at the zk proofs workshop where a lot of you will also be. I guess was it in 2 weeks? So I hope we get some more updates there. So regarding the infrastructure, so one of the things to actually make this fast is to have very efficient implementations of cryptographic primitives. So those are typically, I mean, what Alex mentioned. So Rust will be a big part of this project. What we've been working on for the past couple of years is this hex framework, which used to be hexspec. So it's a language for specifying high assurance cryptographic software, which came out of the hex workshops, which is also part of real world crypto. And this has recently been extended to a whole hex framework, so which now supports most of Rust and then compiles to a number of backends. I have a small picture here, but I have a bigger one on the next slide. And combined with this, we've provided the libcrux library, which is a library that collects. The issue was that before we had a number of verified cryptographic libraries. So Heckle from F-star, Fiat Crypto from Rocq, there's Spill, which is verified assembly, a number of others. So what we've done is to specify them in this hexspec language, which is a functional subset or a subset of Rust with a functional semantics, and then embed them into these provers, so into F-star, into Rocq. Then we prove them equivalent because we get a non-idiomatic embedding. So you prove them equivalent to, for instance, the specification of Fiat Crypto or F-star, and then from there on you can use the verified compilers inside these prover systems. So we actually have a proof that you get the right implementation. The other thing is that it's also easier to compare code across provers. So yeah, so that's the way we want to include very fast implementations of cryptographic primitives into the certiCoq pipeline. Let's go to the next one. So the main insights from Hex is that we want to move, and this is work together with Kestrel company. So that's a spin out of INRIA. So the main insight there is that we want to have a tool where the software engineers can actually work directly on code that's familiar with them. So that would be Rust. And then the proof. So this is translated to tools that the proof engineers work. And the cryptographers can also look at the Rust code directly, because cryptographic engineers are typically used to Rust or won't have much problem reading it. Then once we have the embedding of this Rust code in these proof assistants, we can prove correctness, for instance, using Rocq or F star. By now, we can prove panic freeness in a mostly automated way in F star already. That can probably be duplicated in Coq, but that hasn't been the emphasis. We can do proofs in the symbolic model of cryptography using ProVerif or CryptoVerif or dy star. That's the Dolph-Yao model in F star. What we've been focusing on in my group is this SS proof here, which is a framework to do game hopping proofs, or a modular version of game hopping proofs. So this came from the TLS verification, which is a part of the Everest project. So this is a new way of writing cryptographic proofs, which has also been popularized in the book Joy of Cryptography. And so this proof of writing proofs on paper also is becoming more and more popular. For example, both the TLS 1.3 but also MLS have been written in this style. So that makes it a really good way of communicating with the cryptographers about writing the security proofs. So there's a list of publications here in for the Hex toolchain. And then, so this is the usual way of working with this code. So you write your program in Rust, then you verify the correctness, you verify the security, either symbolically or in the computational model, and then you have a proof of security and of correct implementation. And we've done that for a number of protocols, and we're still working on more and more. Then going to zk proofs. So we'd like to specify also these zero knowledge protocols using HexPack. That this is feasible has been shown, for example, by my master students some years ago. So we started to look at this Halo 2 protocol because there was a very nice Rust implementation. There was also a Halo 2 book which tried to reflect what was happening in the Rust code. So what they did was to write HexPack, which should sit precisely between the two, and actually found a bug in the book. So I would hope that in the future it's possible to just to write, if you actually want to write a well-documented Rust implementation, that we can do it using HexPack or Hex. And we'd be happy to help people do that. We've been doing zero knowledge proofs in SS proof. So there we did the Schnorr protocol, for example, and some other protocols. So we have a framework for doing zero knowledge protocols in SS proof already. I've also worked on doing the zero knowledge protocols in EasyCrypt, where EasyCrypt, of course, also a very good tool to do that. The previous version of Hex supported EasyCrypt, and it wouldn't be too hard to do that again. So that might be another possibility. So currently, what's working, what we've spent most time on is connecting to SS proof, because then you can connect to the wider Coq ecosystem. But you don't have a lock-in, so you can with minor effort also target EasyCrypt or potentially other tools. Then finally, we want to, as I said, we want to integrate libprox into Certicoq, so that we don't need to re-verify the whole of, say, the Heckle library. And we do that by the embedding of using hex, we can embed the specification of the Rust code, and then once we actually compile, we can replace them by the optimized implementations because we proved them to satisfy the specification. One could perhaps go even further. So there's this project Verify, which does verified verified C calls from certicock, and we could try to do something along the same lines. But as a start, I would just like to include libprox into certicock. That's sort of the overview of what we plan to do.
Okay, thank you. Any questions, I guess, from anyone about this? And then otherwise, we'll move on to quickly presenting the other formal specs that we have. Okay, so I guess, so in terms of formal specs, we've got 4 which we can quickly introduce. So I guess we'll do it in the following order. Maybe Ramana can go first and talk about his Hall 4 specification. Kestrel can go next and talk about the ACL2 specification. Someone can Nethermind can go right after and talk about their lean spec. And then Guillame from Formalland can quickly talk about the work they've been doing on an ESP grant to match REVM with the Python EVM spec in Rocq. So I'll let Ramana go ahead.
Awesome. Thank you, Alex. Can someone just confirm that you can hear me and you can see my screen? Yeah, yep. All good. Yes, I'm going to talk about Verifereum, which is a project that I started a couple of years ago, but it's starting to take off a bit more now, which is for formal verification of implementation correctness for applications that run on the Ethereum virtual machine. That's the main target goal of this project, but it's intended to be kind of a long-standing and multi-purpose formalization of the EVM, both for compiling to the EVM and compiling the EVM itself, for example, to zkEVMs. This is potentially within scope as well. We have this nice website that explains at a high level, what the purpose is and why we're doing it. Verifereum.org. So just for now, to go quickly, I'm going to say a little bit about what we have so far and where we're going in the nearer term. So the main focus for now has been an EVM semantics in Hall 4, which is phrased as this easy-to-read monadic functions in logic. I think it's going to be quite similar in underlying style as the K semantics. I think I was going to show you just our GitHub to get an idea of what this looks like. So if you go into the Verifereum GitHub in the execution scripts, this is one of our Hall 4 theories, and you can see that I'm going to stop somewhere, maybe here. Like here's an example of one of the operations. It says pop the stack, this is for the exp opcode, pop the stack, get the base, get the exponent off the stack, and calculates the gas, consume the gas, and then it runs the underlying, like shallowly embedded word operation in the Hall 4 machine word library to compute the result and then push that onto the stack. And we have implementations of all of the opcodes like that. And at the end, you have this big step instruction function that calls out to all of those opcodes, all those opcode implementations. And then we have some functions on top of that. Like this is the run the step thing repeatedly, and then some post-transaction accounting for deducting the gas from the sender. And ultimately, we have something like run a bunch of blocks. So all the transactions in those blocks is a fold over this run function. And we can also run it to compute the state root of the resulting state, whereas this one will compute the resulting state in full. So that's like a very quick, just to get like an idea of what the semantics looks like. I think I can also show you that well, maybe I'll go back to my slides first. Yeah, we have passed all of the major functionality in the test suite at the Cancun revision. There's still maybe a few tests missing because there's some precompiles missing, and like that's just still work to do. but to show you what it looks like, we can prove theorems. Like this is a theorem about that run blocks function that says if you run the blocks that were extracted from the JSON block hash tests.json, for example, we extract those from the JSON, define them in logic, and then execute this function, and it produces, one of the things that it produces is the post state that was also extracted from the test. So we have theorems that say that the tests pass. We've also started proving some other things about the semantics, like we proved that the semantics strictly consumes gas, like the amount of gas left goes down, and hence that's every time you run the semantics, it terminates, and this enabled us to prove that that loop of running the step function over and over terminates. And maybe some more interesting properties are separation properties, which we show that if you have a theorem like the one I showed you here, this theorem actually says that there's a domain associated with it, which is all of the addresses and storage keys that are touched during that execution. And we have a theorem that says if you were to run that execution in a state which had other stuff in it, like there were things outside of the domain, it would produce the same results, and those other things would be untouched. And yeah, we want to kind of use this thing as the basis, these separation properties, to start to build like a separation logic as the basis for doing verification on top of this EVM semantics. We're just getting started with proving properties about the semantics. Obviously, to get to the point where we're able to pass the EVM tests, we've done a bunch of auxiliary formalization work, for example, RLP, Patricia trees, Merkle Patricia trees, all the hash functions. For the hash functions, we don't have so much proofs about them. It's more just getting the implementation defined in logic. And this is my last slide. This is about what we're planning to do, where we're going with this. Maybe the headline item is verified compilation for Viper. So we have a grant that's funded to do the formal definition of a subset of the Viper language, and I'm working on that at the moment. That's also in the Verifereum GitHub organization. And the like guiding star for that is to have a production grade verified compiler for Viper, with perhaps some milestones along the way, like just getting a verified compiler, but maybe not production grade from Viper to the EVM, applying for funding for that at the moment. And then the other direction for verification of applications is where we don't do verified compilation, so we don't care about the source language of the application, and instead build a separation program logic for arbitrary EVM bytecode applications, and build some proof automation around that. So the ideas there currently are to do proof producing decompilation into logic in the style of work that was done by Magnus Myrene on machine code decompilation for kind of normal CPUs, but in this case, we'll do it for the EVM machine instead. And that has been used to verify like very big applications, including a theorem prover for ACL2 called Milawa. Yeah, so this is kind of in an exploratory phase, but there is some work in the repo which you can find. I won't show it to you now, just for time. And there are many possible other directions as well, including verified compilation using KEVM or perhaps Pancake, which is like a more low-level version of the backend of the KEVM compiler, to do verified compilation of the EVM. So most of what I talked about before was verification to the EVM, where the EVM was the final language, and so we were more verifying the application on top, but this would be checking that the EVM implementation itself is correct. And we could produce perhaps a fast implementation of the EVM in machine code in RISC-V, for example, or any of the other targets that KEVM targets. And then I just wanted to mention that this is a free and open source and public project that's open to any people to join. That's why it's all got this website, got this GitHub, and we have our discussions on Zulip and very welcoming of new collaborators at any time. And yeah, now I'd be very happy to take any questions about what I've been talking about. Thanks.
So just a very naive question. At some point, there was a discussion of going from Viper to the FE or free language. I mean, it's a pun on Rust, and it seems like it's that project was abandoned.
Yeah, I don't know about it. I've been in touch with so I'm working closely with the Viper developers, and we're just going directly to verify the compiler without this previous projects. But I don't know.
And so is the Yule intermediate language, is that used in the compiler?
No.
No. Another question. You mentioned separation logic. What kind of separation logic are you using for the compiler? How does it come?
I think we're not. So the separation logic was not so much for the verified compiler, not for the verified Viper compiler. It was more for doing verification of EVM applications directly on top of the EVM semantics. So instead of doing verified compilation for your application, this would be using a separation logic and probably a lot more infrastructure to prove properties about bytecode programs out there in the wild. So we wanted to like take compiled contracts that are already running on chain or about to be deployed on chain, and directly verify the bytecode implementation of those contracts using a separation logic that is to be designed and to be kind of adapted to this purpose and built within the theorem prover.
There is a separation logic for EVM that was done in Isabelle. We could have a look at that. You're probably aware of that.
Yeah, I think that was done at Data 61. I think I knew some of the people who were doing it when I used to work there.
It was quite some time ago. I don't think it's maintained anymore. But in any case, I developed the separation logic. Of course, there's a big. I mean, the Iris project is a big separation logic in the Rocq theorem prover. So that's something that we might want to use at some point. But it's certainly not.
I'm aware of these projects. I haven't looked in too much detail, but we will take inspiration from them as needed, for sure.
Thanks.
Okay, then I guess, Eric, do you want to go ahead and talk about the ACL2 spec?
Yeah. Let's see. I'll find the right window here. Okay, do you guys see these slides?
Not yet.
Not yet.
How about now?
Yep.
Yep.
Great. Okay, so I just wanted to mention some of the work that Kestrel's been doing about Ethereum. A lot of this was older work, and we're really hoping to get back into it. So we have a partial formal model of EVM in ACL2. Covers a couple dozen instructions. It was kind of a side project from a previous project that we'd really like to extend. And it follows an approach for modeling these kinds of things that has been pretty well trod in ACL2 for really 2 or 3 decades now. And I'll talk a little more about that on a later slide. Similarly, we have now a RISC-V model that Alessandro has created. And we think that would also be an important component of this project to model the semantics of that, all within ACL2. We have a bunch of tools that are relevant. Probably the main one that I want to talk about is my AXE toolkit for binary analysis. I've been using this to verify x86 binary code using the ACL2 model of x86. And it should be pretty straightforward to adapt that to reason about RISC-V binary code, just because a lot of the core AXE tools are sort of language agnostic. It was initially developed for JVM, then adapted for x86, and we could adapt it again for RISC-V. I've used that to verify implementations of things like AES and Blake2 and Cha-Cha-20 and so forth. We have a lot of cryptographic specs. This list probably isn't even complete. We've got basically in the ACL2 community libraries where all of this stuff lives, there's this crypto library of lots of different crypto specs that we've been developing over the years. Other stuff, RLP, Merkle-Patricia trees. Just put the verified Yule transformations on here that Alessandro and Eric had been working on another grant. Maybe I'll skip. We have a whole bunch of tooling for R1CS, including a special version of AXE for R1CS, but let me skip ahead. We formalized part of the EVM, and in the process found some issues with the yellow paper that we fixed with pull requests. And this is a common theme where I'm sure you've all seen this, where you try to formalize something and you have to really, really carefully understand what it does. And in the process, you realize, hey, what does it actually do in this case? This is unclear. This is contradictory. So just a side benefit of formalizing is that it often can crystallize, what exactly all these things mean. Just a little about ACL2. It's a mature theorem prover developed since 1989 and actually has roots that go back, I think, almost 50 years to the Edinburgh Common Lisp pure Lisp theorem prover. It's industrial strength, lots of use in industry. It's general purpose, so you can prove pretty much whatever theorems you need. And one of the nice things is that we can do everything within ACL2 using the different models that we have of EVM, RISC-V, x86, JVM, whatever we need. We're also building models of source languages like C and Java. It's very automated, rewriting and induction are its main tactics. Also has efficient execution. So this is maybe a little bit difficult because you'd like an applicative, purely functional language, but you also want to do things really fast using single-threaded destructive updates. And ACL2 has a whole story about how it can kind of get the best of both worlds there. Lots of powerful add-ons, including ACKs, connections to SMT solvers, and then a very rich and active community with thousands of commits per year into the community libraries. So I mentioned this modeling approach. Basically, this has been done for lots of different either CPUs or machines, if you will, over the years, starting with things like JVM and then the x86 model that you may have heard about from UT Austin that Kestrel has also worked on, and now EVM and RISC-V. And our approach is basically to write an executable formal simulator. So it sort of has a dual nature. On the one hand, it can execute, and actually these things in ACL2 tend to be fairly fast. The x86 model that UT Austin created can run something like 1 megahertz. And actually some recent news is that it can now boot Linux. So you can run Linux inside of ACL2 on the x86 formal model. So we think that's pretty cool. But on the other view, it's a formal artifact, a mathematical artifact that you can prove things about. You can prove lots of different well-formedness, termination. You can verify optimizations to the model. Say, here's the nice version, here's the fast version. I prove that they're equivalent. So you can reason about the nice version and run the fast version. Just whatever you need to prove, because it's a general purpose theorem prover. And then you can use these models to verify binary programs. Typically, that's done by rewriting base symbolic execution, either with ACL2 or with ACKs, where all the simplification rules you can prove ahead of time as ACL2 theorems, so that you know that when you're applying these huge libraries of hundreds or thousands of simplification rewrite rules, you're not doing anything wrong because you prove them all ahead of time as theorems. Effectively, this is kind of like the Magnus Myrene approach of lifting the program into logic. So you might take some binary for x86 or RISC-V, lift it into logic. You might take a specification and then do an equivalence check within ACL2 or within ACKs of those two artifacts. And we've done this for lots of different programs, especially crypto algorithms. Just to show you one snippet from our EVM spec, this is how we model the add instruction. And actually, this is generated by a macro from something even simpler that just basically says add the two things, and then it adds this boilerplate stuff. So there's a very strong macro system within ACL2 that can automatically generate lots of boilerplate stuff. It's probably not surprising, but this is the kind of thing. We have this for a couple dozen instructions. We'd like to flesh out that catalog and compare notes with the rest of you who are doing similar things and have models that are well tested, and make sure that we all agree on what some of the more exotic instructions actually do. Then we would cross-check that with RISC-V implementations using this kind of tooling that I've been talking about. Any questions on any of this?
That's very cool. Thanks, Eric. I don't know if it's a question, but more like still very interested in doing a cross-checking formally of your models, of your instructions and ours.
Yeah, so we have this, just for the rest of you, we have this connection that existed before connecting ACL2 and Hall. And we've been working a little bit on reviving that. And I think actually I worked with Matt Kaufman on the ACL2 side. I think there may be some work. Conrad Slin was interested in it, and I know you are as well, to revive the Hall side of it. And that would let us do some cross-checking of these specs. We're also interested in other things like having a SAIL to ACL2 connection. In the past, we've wanted a K to ACL2 connection or ACL2 to K, which would be really great. These all seem doable, and it would be really good to, there's the level of, comparing informally. Okay, how did you guys model this? I've been asking some questions about this, like what does Blake 2 do in this weird case where the RFC seems to have an overflow? I found another weird one with Cha-Cha-20 the other day. But then there's the formal, like, okay, can we actually import one system's artifact into the other system and do an equivalence check within that system, which I think would have a lot of value as well. Someone asked, is this where the EVM stuff lives? Yes, that's where it lives. But it hasn't been updated in a few years because we haven't had any funding to work on it. So it's still there and it's being maintained, but it needs to be extended to have all the other opcodes, including the more interesting and complex ones. I just did sort of the easy ones because it was kind of a side project.
Yeah, thanks a lot. And yeah, hopefully we find some good targets and good reasons to get some funding for that and getting everything up to date. Same as for the Horsefall spec and the other specs. Okay, so I guess next, in place of Julian being here from Nethermind, whoever from Nethermind wants to perhaps talk about the Nethermind spec in Lean, feel free to unmute.
Hello, everyone. I'm Petar from Nethermind from the verification team. And I don't have any slides, but hopefully it will be clear enough, the discussion, and then we can also have questions. So basically at Nethermind, we have built an executable model of the EVM in Lean. And the way we've done that, like in the first instance, was to model the yellow paper as faithfully as possible. And we were using the official Ethereum test suite as the ground truth. As most of you know, this doesn't quite work that well. And we had to make many adaptations to the functions from the yellow paper in order for the tests to actually pass. And now we are only not passing 3 of the 22,300 and something tests. And one we know what to do with, one is incomplete, and one we cannot find a person who knows anything about it. So I think we're pretty much there. We also have an executable model of Yule, which reuses the primitive operations of the EVM that come from the EVM model. So basically we have a unified implementation of primops, and then depending on where we want to use it, the implementation forks, and basically goes one way or another. The executable model of Yule will in future likely be used to power our formal verification tool Clear, which verifies basically programs that compile to Yule. Also to say, in the last few iterations of the tests, when we were trying to figure out what to do about them, we had extensive help from looking at the KEVM formalization, which seems to have ironed out the very complex details that were sort of not clear. So if anyone is missing some tests, I would recommend either going to us or going there for some clarifications. I'm not sure what else to say. Franciszek is here as well from Nethermind, and perhaps if there is anything that I've missed, or if there are any questions, we can answer them.
You haven't missed anything, but yeah, more than happy to answer questions.
So yeah, one question I have actually is, your model is executable, but obviously one quirk of Lean is that at least at the moment, it doesn't always produce very fast code. And so I'm curious to whether you've tried to benchmark anything yet, or if it's just at the status of executable, but obviously far from being very performant.
Okay, so this is actually sort of very fortuitously something that I have spent the last week on. And so essentially, we struggled initially with some of the, especially precompiled and some of the more complex implementations we sort of had to also implement in terms of FFI to get some reasonable speedups, but that's the obvious stuff. And in terms of like how quickly we can get the conformance suit to go through, there is a slow test essentially, or like a couple of slow tests that do like 10 million iterations in some of the EVM/performance tests /loop mul tests. And the slowest test is like 38 minutes. However, if you sort of parallelize the rest of the conformance suit and all that, then you can be done within an hour on a sort of normal, regular Joe computer, which is more than acceptable. So the performance is like, look, the tightest loop that there is like 38 minutes. It's a lot of arithmetic in like a lot of iterations. So it's not terrible. Does execution in Lean produce theorems? Does execution in Lean produce theorems? So as long, so yes and no. So basically, as long as you keep to Lean, yes. However, the moment you actually reach into FFI, then of course not, right? So yeah, but you can extract executable stuff, right, from constructive theorems.
And just to say that we will be applying this week to upgrade the infrastructure to Pectra.
Oh, that's a good point. Yeah, likewise, we put in a grant application to upgrade to Pectra. But I mean, the intention is to at least formalize the live schedule at all times, and possibly some previous ones too, but at least the live one. I think might be worth mentioning that one of the cooler things Lean lets you do, I'm not gonna lie, I haven't used Rocq for a good decade now, but what you can do is that you can have like a nice Lean sort of an equational axiomatic representation of something, so a Lean definition. And at the same time, you can say that, oh, by the way, use this one for reasoning. However, whenever you want to compute with this, use a native implementation. And this, of course, we cannot prove equivalence between like a C implementation and a Lean implementation, but you still do get a sort of a nice bonus, right? Which is, hey, I can reason with this one in Lean. However, when I need to run this, I'm not gonna, like do this horrible recursive version in Lean. I'll run a quick C implementation or some such.
Yeah, I'll just read out Marius's question from the chat for the sake of people who watch back the recording of the call and don't have access to the chat. So Marius was asking what specific in Pectra that you want to update to, and are you going to cover precompiles and system contracts? And I guess Ramana or Petar, you can just read out whatever you typed in in the chat.
Yeah,
I think Petar's answered yes. Like there's a bunch of EL execution layer changes in Pectra, and both the Lean and Verifereum's specifications of EVM are intending to implement them so that we pass the Pectra test suite. Yeah, we're genuinely going for like the 100% conformance tests with like an asterisk. Like, look, if we cannot get one test right because we cannot find a guy to actually tell us what it's supposed to do, that's the asterisk. But we are going for full conformance. So I had a question that's maybe not so much for the Lean team, although tell me what you know, but it's more like for Alex or someone else here. Who is responsible for the test suites? Are they on the call? How do we talk to them?
So this is a good question. I don't actually know. Maybe Marius knows. I did try to get someone who works on EELs to come on the call, but unfortunately, it basically clashed with them having a fairly long holiday and some other events. But yeah, you're not the first person to ask. And yeah, Dimitri,
there's two test suites actually, and I think both of us have focused on the legacy tests. But there's an effort to make a new test suite and potentially to port everything over. And so the situation might get better when more moves to the new one.
Yeah, that would probably help. But yeah, that should be probably something that we can figure out.
Yeah, so I can I can probably enlighten there because I was for a long time kind of the person responsible, because no one else took it over. We've had this Ethereum/tests test suite that is kind of, yeah, it was maintained by Dimitri from the EF, but it's being ported over to EELS, and the new testing team is led by Mario Vega, and he's been building East tests. And the problem with porting all of these old tests is that it's like 20,000 tests or something at this point, and they just need to be they're a very weird mix of edge cases that someone found at some point. They're written in multiple different languages, different programming language, like different EVM languages. Some of them are in bytecode, some of them are in LLL, if anyone still knows what that is. Some of them are in UL, some of them are in Solidity. And so, yeah, porting them is just a pain, but that is a project that's been going on. I'm specifically wondering about Pectra because I think in Pectra there are no changes in the actual EVM itself, except for the new BLS precompiled, and the big changes to the EVM or like to the consensus in Pectra is actually in this outer envelope of the EVM, like for example the set code transaction, the system contracts, all of these things that are not really part of the EVM specification itself, but also interact with the consensus.
Yeah, so there's a reason why I would say, even though I'm focusing on the execution layer and not really modeling the consensus layer, these system contracts and things do show up in the specification. And the reason is that, well, I have that top level function, which is run block or run blocks. And when to get the output state to actually match with when you run some blocks, you do need to do things like update the contract that has the beacon roots, and you need to have all the system contracts available in case they are called and so forth. So that's why it does actually show up.
Yeah,
sorry, go ahead.
I agree that it shows up. I'm just wondering are these things already part of your
Yes.
of the models that you run? Okay, interesting.
Yes.
Because that is, it should not be a big lift then to move to this new to add these couple of system contracts.
Okay, so just we can probably go on about this a bit more, but I'll just try and get Guillame to quickly talk about their formal answer work on getting REVM compared to PyEVM using their kind of Cocker Python and Cocker Rust tooling, so that way we've got all the presentations done, and then we can go on with the conversation. So yeah, go ahead, Guillame.
Are you speaking, Guillame? You're
yeah, so we can see your screen, but we can't hear you.
I don't know if you can hear me now.
Yeah, now it's good.
Okay. Yes, so we work on formalizing the REVM implementation in Rocq.
So now we can't see your screen though.
Okay, I'm sharing again. Sorry about that.
No, it's...
we want to have a Rocq semantic for both the REVM and the reference implementation of the EVM in Python, so that we can compare the two in all kernel cases. So Python specification is optimized to be the simplest possible one. There are around 3,000 lines per version of a protocol. I think it's quite short. And for the RISC-V it's optimized for speed. So that's why I think it's used for now by most of the zkEVM to implement the EVM specification. But it's also much larger, and the code is tends to use advanced features of Rust. Our general approach is to have first a manual translation of the two code to the Rocq system, where we have a idiomatic Rocq version so that we can easily prove the equivalence between the two. This is a work that we started last summer on a few instructions. Here is, for example, how you can translate the div operation from Python to Rocq in a similar fashion. And we can do the same work for the Rust version. But a big issue is that it's hard to get right all the instructions, especially the advanced ones like precompiles and calls. We can easily make small mistakes. We have done many mistakes when we review our code. And also it's hard to follow upgrades because when there is a code change that is made across many files, in our experience, it's very important to have automated tools to make sure we didn't miss anything. So that's why we have a grant with the Ethereum Foundation to use the Rust tool to do this translation automatically from Rust to Rocq. And this is what for the div operation the tool generates. So it's much more low level. The question is how to go from this low level translation to the more idiomatic Rocq code that we wrote. And for that, we work by refinements with two steps. The first step where we add back the type and name information, and the second step where we handle the pointers of Rust to translate them to a state monad. So we are mostly working for the links now with a lot of automation tactics, and we are starting to handle a few instructions. For example, here's the script to handle the edition. And the script is much smaller than the translation of the addition, and we can now replicate it on all the operations. And for the simulation, still in progress, we have a few primitives where we can translate up to a state monad. And our hope is to have at the end of March the 80% of the REVM, but we can translate to a clean version, a purely functional version in the Rocq system. And after that, the goals will be to show that our idiomatic version written by hand is equivalent to the purely functional version of the code that we translate from the implementation, and also to do a similar work for Python. We have a beginning of translation for the core of Python to Rocq. We need to work more on it. And yes, I'm open for questions.
So there's one question in chat from Ramana, which is whether this is the same project as what Karl was talking about earlier about also verifying RVM. And I guess the answer to that question is no, but obviously there might be some tie-in at some point.
Yes, yeah, I hope that we can show code equivalent to the EVM implemented in the Karl and Bas project. And yeah, for that we we are waiting for them to be completed, but I think that's a good thing to do. We can maybe forget about our project of making our own idiomatic version of EVM.
Yeah, I think the general gist is that the EVM specification is supposed to be more high level, right, than kind of what you get from Python. But obviously, it would be nice some kind of validation for the high level specification that you can prove it equivalent to a lower, sort of more operational specification, you could say.
Yes.
Okay, thanks. So I think that covers all the presentations we had planned for today, and we're obviously already at about an hour and a half, which was the time that was allocated in the calendar event. But I think if anyone is still keen, we can have a bit of discussion. And I quickly want to kind of recap, I guess, the kind of key things that I have in mind with respect to all this work. And one of these is obviously extending form verification to more clients than RVM. At least on the Rust side, Lambda class is working on an EVM client, and they have LEVM, which is progressing, and probably I think soon will be pretty much stable and pretty performant and a useful Rust alternative to RVM. And then obviously we have other clients in other languages, and support for that kind of depends on the zkEVMs actually supporting the different languages that every client is based in. And so we can talk a bit about what it would mean to make an effort to verify multiple clients and keep multiple clients verified in parallel, using different teams working with different specs would look like, and obviously a sense of what I would like, I think, both economically, but also in terms of either having more automation as well as potentially embedding that form verification task into the development process. I think one issue with the specs is often that, well, for one, we basically don't have a canonical spec. In some cases, guess kind of functions as the spec, but it's obviously written in idiomatic Go and heavily optimized. And so other than the fact that obviously it shouldn't be the spec anyway, it's also not great as a spec because it's not meant to be. The Python specs, I think sometimes they're a bit out of date. And then we have a mix of following the yellow paper, looking at the K spec, looking at other specs for inspiration, and kind of doing things in a slightly ad hoc manner. And it would be nice to get a sense of what the best way forward is in handling multiple specs is, and keeping multiple specs up to date constantly, which is obviously some effort, right, both in terms of time and resources required. And then the other question is obviously whether there are options to get, fast code generated from formal specs, and how much effort to put into that based on how realistic it is that you could get an actual code base generated from a formal spec that's fast enough for people to run it, and whether that could be embedded into bigger clients, right? So the EVM is a small part of a fully fledged Ethereum client at this point. And so you would have to figure out how to kind of embed that EVM generated from a formal spec into a bigger client. Like Marius said, there are quite a few things even in the EVM that are obviously not part of the spec, and that's also a blind spot for the verification efforts that we're doing. So yeah, I think if anyone has anything that they want to comment on, those are the things I have in mind and I'm trying to think about at the moment. But obviously there are a lot of other things to consider. And yeah, I think an API for calling an EVM engine would be nice. And part of that is also then getting a discussion going, I think, with the different client teams. Not just obviously at the moment, RVM has some verification effort going on with it, and so we've got some ties there. I've spoken to some of Lambda class about looking at their clients. EVM1 has come up, but it would be nice to have maybe a broader channel of communication between the different formal spec teams and the different client teams, that could help both ways, right? I think the client teams would benefit from formal verification, but could benefit from the people writing the specs who are spending a lot of time looking at niche details. And similarly, obviously, people writing formal specs would probably benefit from being able to embed their work into client teams and in the clients that people are running, but also into having, I think, maybe better access to the people who are building a lot of the time updates to the EVM and discussing these on ACD before they even make it to formal specs for the most part. And I'll quickly go on, because I see obviously there's some discussion in the chat of setting up a Zulip chat. I did look into setting up a Zulip chat for kind of Ethereum form verification related things in general. I think a lot of times the vibe is that you can have another Zulip, but then a lot of people also complain about already having too many Zulips. I'm already definitely on too many Zulips. But it's definitely something we can talk about, and we can talk about this on the Telegram group outside of this call. But if it feels like a lot of people are interested, we can definitely do it, and I can definitely set that up.
I think it would be helpful to have it. I mean, it doesn't matter so much where it is, but it would be good to have it to, have kind of more in-depth discussions, this cross-collaboration discussion that you're looking for between the formal methods people and the client implementers, for example, where, we're not necessarily going to be working on each other's code, but we might both have like very in-depth technical knowledge about the same artifact. And could discuss things like, an API for calling the EVM, like Mario said, that Aragon has one, maybe other people we want to standardize around that. Or maybe like this issue of the test cases, where there's some tests where it's just like, well, get passes it, because get generated the test output actually. But we want to like get into the details of what's going on with that test.
Yeah, so I think one question, and this goes, I think, maybe for Mario specifically, because you'll know exactly how that process works, but the client teams, as I understand it, have a kind of yearly retreat or a retreat before hard forks or something like this, where every client team gets into the same room and they kind of stay locked in until everything works together. And I don't know if there should be a discussion of, should that include people maintaining formal specs, at least, kind of formal executable specs that could essentially function as part of clients, or whether we should have the same process for teams maintaining formal specs. Everyone gets into the room until everyone agrees on what the spec is. But that could also be something to think about, right? To have these somewhat periodic meetups of kind of forced interaction until things work. And that could be a way to get closer to having specs that we know are consistent with each other, if we're not going to have a kind of fully canonical spec. And I don't know if Maris, if you have any feedback on what that experience is actually like. Presumably you attend these events pretty regularly.
Yeah. So the problem is that these events are already extremely big. It's like, I think 150 people at the last one. So it was already a bit oversubscribed, and that made like some of the like discussions kind of hard. So I don't know if it's beneficial to add more people. Usually it's also more about the like getting the stuff to run, and everyone should bring like their fully implemented client to the to the event, and it's more about like having the interoperability between the different clients. And yes, the testing people are there, and the specification, like the yields team is there. Yeah. And so one comment to EELS is that like they've been kind of lagging a bit behind the official hard fork process.
Yep.
But that is something like they are kind of a small team. I think that 4 people now, 4 or 5 people. And and they recently hired like there were only 3. Now they hired like a 4th one, and they finally kind of caught up to the head. So they, for example, already have an implementation of EOF live in the East, and so yeah, in the future we would like to go to this. In EOS, but we also have tests for EOF in East already. So in the future we would like to go to this process where everything is implemented in EOS and East before we even schedule it for part 4. And so that would also mean that like that gives like alternative EVM implementations the time to update before it goes live in minutes.
Yeah, so I think this actually goes on to the next question I had, just kind of a bit more related to you and your work, which is at the moment, Guess kind of leads the way. And so presumably you never essentially look at a spec to implement something because you might be the first ones to actually implement it. Do you have a sense of...
That is not true. Like this like non-spec driven development, that is kind of a thing of the past, I think. Like in the last 2 or 3 years, we've become way better at looking at the spec and like also maintaining the spec and updating the spec. Also, unfortunately, it's not always Get anymore who is like on the forefront of innovation. So sometimes we also implement the spec of other people.
Yeah, but I guess the thing that I was leaning into was whether you would find it useful or whether you'd essentially like to have formal specs to look at as opposed to informal ones, and what kind of value you see in formal specs for your own work as opposed to just to formally verify what you're building.
So sometimes the problem is that like sometimes the people just write like formal spec or informal spec, but it's pretty shit. Like it's a good spec, but it doesn't make sense when you actually implement it. So a lot of our time is actually spent on iterating over the specification with the researchers and other client implementers. For example, like the 3074 specification was interesting, but in the end we kind of decided, okay, let's not do this and let's do 7702 instead. And then like there was a bunch of underspecified things in 7702 that needed to go through this process of like figuring it out and specifying it. The problem is it is extremely hard to write a specification for a new feature in the EVM because the EVM is so large and there's so many edge cases, and you need to think about the gas consumption, and you need to think about like memory expansion. You need to think about all of the all of the modes, how a contract or an opcode could be executed. Like, is it executed in the same like in the context of a contract? Is it executed in the context of init code? Is it executed in the context of a delegate call? And all of these kind of weird edge cases. Yeah.
Yeah, that makes sense. I don't know if anyone from the different formal spec teams wants to jump in, and otherwise we can move on to something else.
Just one thing is that if there is interest in formalizing things before they become live, to check, to make the specs better and to see that they're implementable and stuff, like I'm capacity constrained, but apart from that, very interested in working in that way.
Yeah, I think it would basically be interesting. And I know, so I talked to I talked to the EOS, some of the EOS team at DEF CON. We had a layer 1 R&D workshop there where they had a breakout. One issue tends to basically be that a lot of people write EIPs and want their EIPs to be, included in a fork and whatnot. But obviously, there are much fewer people who actually want to implement a spec for their EIP. And so I'm not sure what exactly the better of dealing with that would be. Obviously, the choice of EIP inclusion is one thing, and then the process of writing the spec for it would be another, and whether those two would be fully independent is hard to say. You might want to have, for certain EIPs, you might want some kind of spec before you even think about including it, right? And then obviously whether there would then be a bottleneck if you're working off of a formal spec that very few people can write. For example, if it's Hall 4, there's you could write it. There might be a few other people who could write it, but obviously it's a kind of constrained amount of people compared to something like Python, right? And whether that would add either more slowness to the system, or if it would just mean that actually people kind of have that effort to the side and ignore it in their own development, or kind of don't wait for it to happen to do their own work implementing it in a client. There's a couple open questions. I think it would be interesting to think about it and explore how it would fit into I guess the ACD process to get a sense of it. But it would be interesting to have, right? It would be nice to have specs in advance of things launching, and it would obviously be nice, for all the efforts that we're doing to verify clients, if at the very least, once we have the fork and reach mainnet, things should be formally verified by then, if not before testnet. And yeah, I mean, in terms of spec writing in some easy to use DSL, so there is actually something I can say about this. We've been looking at this for the consensus layer. So the consensus layer also has Python specs, but the Python specs to the consensus layer are very much closer to being, official canonical specs than EOS or any of the spec in the execution layer are. We've been thinking a bit about how to formally verify the specs themselves as a consensus layer and verify certain properties. We haven't settled exactly on how to do it. So Roberto Saltini recently joined the EVF from Consensus and is thinking a lot about this, and we're talking about this together. We thought about setting up a Python to possibly lean kind of embedding. They use basically a specific subset of Python to write the specs, which is a bit nicer than kind of just using vanilla Python. And it's meant to be kind of very much non-idiomatic and as readable as possible. If we run some experiments with respect to that for the consensus layer, and it seems like it's working well, we could try and extend that to EOS, right? And just have EOS as, really being the official spec, and then being able to extract this into some proof assistant. And then from there, we could work on equivalence with other proof assistants. That would be one option. We're not yet settled on exactly how to do it and exactly what the effort of doing that would be and whether it would be worthwhile. But obviously, as we're gearing up for a lot of spec writing as part of the beam chain effort for the consensus layer, we are going to be, I guess, experimenting with that pretty soon once the spec writing for that starts. So yeah, we'll see about that. It would definitely be nice to have a better link from an easy to read, easy to write spec language like Python to proof assistance and formal specifications. But it'll be a bit of effort to get that done.
So why Python instead of Rust?
So one reason is essentially that the client teams all have obviously different languages they use for the implementation, and Python is a fairly neutral ground that everyone can read fairly well. It's fairly easy to write non-idiomatic Python that's quite readable. Another reason is actually purely that to write the specs, you usually have to involve quite a few people. and Python is the easiest language to involve people in. So, I mean, I'll talk about the beam chain effort specifically here, but one idea that Justin had was to get as many people to contribute as possible. So possibly you would have people contributing a single function to the spec. If that's the case, then I think Python is really the only language that kind of makes sense, because it's the one that's most accessible for people to contribute to. So there are obvious trade-offs. Yes, it's a similar reason the call is in English. There are obvious trade-offs, and it is what it is. And there's this obvious constraint of at the end of the day, the people who write the spec have most of the say on what language the spec is written in, and so to some extent, it's also historical reasons. But for the most part, I think developers find the Python specs easy to read and easy to understand, and that's the main thing. And then the subset of Python is used for the spec. It should be documented somewhere. I can try and dig that up. But it's basically kind of a fairly narrow subset, and you have kind of annotated types and things like this. If you look at any of the consensus layer specs, you can see them. I'll post that to the Telegram channel after. But yeah, I think any suggestions that people have on trying to link any kind of Python spec to proof assistance, we're obviously very interested in, if only for the consensus layer specs as well.
So my initial reaction to that is that there's nothing special needed. I mean, if you're writing in this subset of Python, even manually writing the definitions in a proof assistant is not that big of a lift.
So I think the main thing is with respect to the consensus specs, like lifting all of them manually to lean or any proof assistant would still be quite a bit of effort. And what happened, I think, last time when they were working on the beacon chain and also I wasn't there, was that the specs kept being rewritten. And so if you keep rewriting your specs and you need someone to also then keep rewriting them in lean as people keep rewriting them in Python, things can potentially spin out of control.
That's fair. Yeah, it would be nice to have an automated generator.
Having some embedding of the Python specs into lean is something that is, I think, fairly doable. I think it's something that even Nethermind, we had a quick chat and they felt it would be a fairly doable project. And obviously you had Everett was talking about a bit earlier about their KEVM to lean effort, and that involves actually some steps that go through Python, and so maybe there's something useful to learn from there as well. But yeah, it is definitely within the range of doable. And then the question, actually, some of the questions we had were around picking a proof assistant that would make the most sense in terms of having more people that could contribute to proving properties of the spec and things like that, with respect to obviously consensus specifically, which is slightly less popular than a few other things that are done in proof assistance. And obviously there's kind of Rocq has a bunch of distributed systems work. Sergey from NUS did a bunch of work on mechanizing blockchain protocols in Rocq. He's recently also been doing kind of similar work with a project called Veil in Lean. And so there are a few kind of interesting things going on there. And yeah, I think the other possibility obviously outside of Python would be something like Sail, which is very nice because it has a lot of tooling attached to it. You get an emulator, you get some testing, you get extractions from Sail to Hall for Isabel, Rocq, and now Lean. I did actually briefly consider writing an EVM spec in Sail for the execution layer. The one question actually around using Sail for something like this is basically, so again, there's a sense of who writes the spec, especially if there's a lot of work involved in writing and rewriting the spec continuously. That means having someone who actually has the time to do it. The other question was actually also around, once you do extract the Sail spec to a proof assistant, whichever one it is, how much can you work with those extracted specs out of the box to actually prove what you want, or do you end up basically rewriting another spec that you show equivalent to the canonical Sail spec and something like this. We've got the RISC-V, the official RISC-V specs, which are obviously kind of to some extent bigger specs than the Ethereum ones, that are now extracted in Lean and waiting to be polished. And actually, Tobias from Cambridge will give a quick talk about this as part of the zkEVM track. We'll see how useful these are when we're trying to prove that obviously, a RISC-V zkEVM circuit correctly encodes, those RISC-V extracted semantics, to get a sense of how it works. If it turns out to work really well, maybe it's worth putting some effort into a sales spec, right? And we'll see about that. But obviously, this trying to do it would be a fairly big project, and it would only make sense to do it if you also had some commitment of being sure you have people to maintain that in the long run, right? At least with the consensus layer, to some extent, the specs don't change. Well, they're going to all change very soon, but for the most part, they haven't changed too much over the last few years. With an execution layer spec, the specs obviously change much more often, and the maintenance load is much higher. And certainly, if it was just me, I wouldn't have time to maintain them. We'd probably have to hire someone or to find a team that can maintain these individually, and then you start maintaining the Python spec, the different client teams, the sales spec, as well as obviously potential grants for the different formal specs and proof assistance, and that starts to add up to having to maintain a lot of things, which is not a problem in itself, but it doesn't really simplify your life either. But it would be interesting to look at, right? Like I like Sail a lot. Okay, so I think we're reaching the 2-hour mark. So I think if anyone has something they want to bring up, now is probably the best time to do it. And then if everyone is happy to log off and to go and drink some water, I'll stop the recording, and we can do another one of these in a while.